This is the first of many videos on acid, bases and buffers, and we're going to talk about Bronsted Lowry acids and bases. Now, Bronsted Lowry acids are a slightly different definition to what you're used to. So they're corrosive, okay, and when you put them in universal indicator, they'll be red, orange and yellow. Weaker acid down here, stronger acid in the red. Okay, and you're used to the definition dissolving water to produce H plus ions. Now, the Bronsted Lowry definition is proton donor. And that's going to be the slightly new part here. The acids that we talk about, generally, it's good for you to know them as stomach acid in terms of HCl, that's a context for where you would find it, and battery acid, sulfuric acid, okay, and then HNO3 can be used to make fertilizers. Now, we also have the weak acid, CH3COOH, which is ethanoic acid, okay, which can be used to make esters and vinegars and such and so forth. But we'll do lots of examples with this through the videos. Now, when it comes to alkalis, you're used again to them being corrosive, and they dissolve in water to produce OH minus ions. Now, they are proton acceptors. So the Bronsted Lowry definition is in the green. So proton acceptors for a base, proton donors for an acid. The ones you're used to seeing are antacids. For example, there are questions all about antacids and they neutralize stomach acid. And you've got NH3 used to make fertilizer, and we'll go through an example of NH3 in a second. And, for example, other metal hydroxides like KOH or NaOH reacting with strong acids to make preservatives. Now, if we move that on to a proton. So what is a proton? So a proton, okay, is going to be a hydrogen, and normally a hydrogen has a proton surrounded by an electron. But if you take the electron away, you ionize it, you get H+. Now, the H+ is only made of a proton. So it's only made of a proton. So when we're talking about proton donors and proton acceptors, this is what we're talking about. So our acids are proton donors, and you're pretty used to this, hopefully, because you've had HCl in class and done these equations before. And you can see there's your proton. It's been ionized, it's been dissociated, and therefore it can be donated. And there is your Cl-. Now, your Cl- is negative, so essentially it could act as a base going back in the other direction if we do it reversible. We're not doing reversible at the moment, but we'll show you in another slide very soon why that matters. Now, there's your proton, so it's a proton donor. If we then look at bases neutralize acids, and an alkali is a special type of soluble base. So it is a base, and the only difference is that it produces OH minus ions. It's a proton acceptor, okay, and here we have our example of it. Now, you could do an easy example with sodium hydroxide goes to OH minus, but I needed to point out ammonia. Ammonia is an alkali because when it's added to water, the proton in water adds on to the ammonia. You can see it's added on here, so it's H3 to H4. Also, a plus has been added, so I've added a H plus from there onto the NH3, and that's called ammonium. At the same time, you produce hydroxide ions, so that fulfills this definition for a alkali, and it's also a proton acceptor, so it's a base and an alkali. Now, if we look at types of acids, there are three types of acids I need to talk to you about, and so the first one is going to be with one proton. Now, it's called monobasic. I always find this really strange that it's not called monoprotic. That's what I used to call it, but they call it monobasic. And the reason they call it monobasic is because of this. Because it has one proton, there's your one proton. To react all of those protons, I would need 1 mole of OH minus and 1 mole of H plus. And that is our neutralization equation. H plus OH minus goes to H2O. So because I need 1 mole of OH minus, the monobasic is referring to how many moles of that base I need to neutralize it, and I need 1. So if you guess here, this has 2 hydrogens and therefore is referred to, and 2 protons, so it's referred to as dibasic. That means you'll need 2 OHs, or 2 moles of OH, to react with all of those hydrogen ions. Therefore, that's where you get the dibasic from. We then move down to our other one, which is our tribasic, which means you'll need 3 moles of OH minus, as you can see here, to fully react with all of our hydrogen. So there's the terms monobasic, dibasic and tribasic. And we'll talk about those in more detail when we're actually calculating their pH later. So now we're going to go into more detail about Bronsted Lowry theory in terms of proton donation. So if you've got here a strong acid, and we just talk about strong acids in this one, you've got hydrochloric acid going to H+. That is its proton that's been donated. Now from there though, because you donate a proton, you leave a Cl- behind. So this Cl-, if it goes in the reverse reaction, the Cl- plus the H+ will go back to HCl. So in going in that direction, it's actually accepting that proton. So the Cl is accepting the H+ and going back to HCl. If that is the case, we can call it a base. So we can call the Cl- a base because it's accepting that proton and going back to HCl. Going in that direction, the HCl is an acid, and it is because it is donating a proton. So when you have an acid, it can have a conjugate base as a result, and that's after it's donated its proton. And we'll go through a more complicated example of that in the next slide. Now, let's have a look at this one instead, because we've talked about conjugate bases, and let's talk about conjugate acids. So what you have here is an alkali, and that alkali has been added to water. Now, water can act as an acid or a base. It can donate a proton to become H-, or it can accept a proton to become H3O+. And hopefully you've tried to draw H3O+ when you're doing your diagrams of dative covalent bonding. So if you look here, NH3 accepts the proton that's in the orange, accepts that proton, and it becomes NH4+, and accepting that orange proton. You see it's OH- behind. So it basically says that it is an alkali because it's producing OH- ions, which is really, really important, but it's also accepting a proton, so it is a base. And of course, alkali is a soluble base. Now, if we go in the opposite direction, so I'm going to come over here now and go in the opposite direction. Now think to yourself, if you go OH- added to the NH4+, okay, you'll go back to NH3 and H2O. Now, that means the NH4 would have to lose a proton to go back to this. So that means it'd have to donate. So that means this NH4 right here can act like an acid if it's going in that direction. So we can get these things called conjugate bases, which are what's left over when you have a strong acid, and conjugate acids, which is produced when you have a base or an alkali. Okay, so if that's the case, we can put this into a slightly more complex example, and the one that you will see in the exam. Now remember, conjugate, the reason we use conjugate is because conjugate means related, so it's usually conjugal right, married. So basically, these two are married essentially to each other. They're connected to each other, right? And that's why we call this conjugate base. It's the conjugate base of that acid. This is the conjugate acid of that base. Now let's look at the most common example you'll get in the exam. So the most common example you'll get in the exam is if you have two acids, and we'll go into further examples of this when we do Ka, but this is the simple example to start off with. And we've got two acids, and depending on which one is the strongest acid, it will donate protons, and the one that's the weaker acid will turn into a base essentially and accept. And you're not used to that because you think that acids just donate protons. But if you've got a stronger acid with a weaker acid, okay, the weaker acid will accept the proton and the stronger acid will donate. So if we look here, we can see that HNO3 has gone to H2NO3+. That means the H has gone from one hydrogen here to two hydrogens here. So that means the HNO3 has accepted a proton. Okay, that means it's acting like a base because it's accepting a proton going from here to here. Now if we then go to the sulfuric acid here, so the sulfuric acid here has gone from H2SO4 to HSO4. So the hydrogen's gone down from 2 to 1. So it's lost a proton. Because it's lost a proton, it's donated a proton, that's acting like an acid. So we know that that's an acid and that's a base. Now let's split it up into what the individual parts are doing. So we can see here that the HNO3 is going to H2NO3+, and we know that that's acting like a base. Now you notice I'm putting in this labeling of base 1 or B1, okay? Because I'm labeling that as the first set of acid-base pairs, okay? And this is our conjugate acid-base pairs question. Remember, you'll get a question that will just say, can you label the correct conjugate acid-base pairs for this reaction, and they'll expect you to put base 1, B1, and they'll give you the labels that you need to do. And they'll put little lines underneath so you can just write down it here. So you can see here, the base 1, because it's accepted a proton, has gone to the conjugate acid of that base, okay? And therefore we label that A1. So it's B1, A1. So the 1 connects them because they're conjugates, and then the B stands for base, and the A stands for acid. Now if you can do the other half, please stop the video and do the other half. But the other half is like this. So you've got the H2SO4. We know it's going to HSO4. We know it's donating a proton. We know that the proton gets accepted up here. That means if it's donating a proton, it's an acid, and we will label it as acid 2. It's because it's the second pairing, not the first pairing, it's the second pairing. And we label it with A because it's an acid. And then we go across here, and we label that as base, as our conjugate base to our acid. Okay, and we call that base 2, or in short, B2. So we've got conjugate acid-base pairs B1 and A1, and A2 and B2. And it makes sense with the B standing for base and the A standing for acid. Remember, these are your conjugates, okay, and they're paired together. And you're going to have to be able to label this underneath and label this. And we'll go through further examples later on where you can just use Ka values to determine which one is the strong acid and do these acid-base pairs. So we're now going to do common reactions of acids, which is a reminder of a first year topic. Now, if you want to go into a slower and slightly more detailed video, you can go into the earlier video in an earlier module which does acids. Just look up acids in the search. This is just basically meant to be a reminder. Now, we've got reactions of acids with alkalis, so acid plus alkali goes to salt plus water. And then you've got sulfuric acid, sodium hydroxide, going to this salt, sodium sulfate, okay, plus our water. Now, if you can, stop the video now, do the ionic equation. So the ionic equation is 2H plus OH, 2OH minus goes to 2H2O. That's because all the spectator ions are highlighted in orange. Okay. Now, what you notice here that it's a 2 because there's 2 hydrogens here and 2 OHs because there's 2 in front of the NaOH. Okay, and 2 waters because there's literally 2 waters. Now, an equation, the balancing in an equation is just a ratio. So it's not an actual number. An actual number would be done if you had a mass and you converted it into moles and such. This tells you if there was, for example, 2 moles, there would be 2 moles of this. So that means if there's 1 mole, there will be 1 mole of this. So it's just a ratio. So we don't need the 2's because it's just a ratio, and the 2's all cancel down. And therefore, this is your ionic equation for acid plus alkali. All acid plus alkali reactions cancel down to that. Another reminder is just for this acids with ammonia to form ammonia salts. You'll do a lot of this in the organic section of the course where you make ammonium salts, but we'll do a simple one here with ammonia plus nitric acid goes to ammonium nitrate. Again, if you want to practice this, just use ammonia and write out sulfuric acid and try and do it ammonium sulfate, or you can do it with phosphoric acid, you can do it with hydrochloric acid. Good ways of practicing. Now, let's go for reactions of acids with carbonates, and they're generally weak bases. And we won't calculate the pH of weak bases in this course. And so acid plus metal carbonate goes to salt plus carbon dioxide plus water. And again, stop the video, do the ionic equation. Now you'll notice that we have highlighted again all of the spectator ions, so they all cancel out and you get your ionic equation 2H plus CO3 2 minus goes to CO2 plus H2O. Again, neutralization reaction because it's creating H2O, just like the other two, the previous ones, were neutralization reactions. So if you look at the other, this one, it produces H2O. You look at neutralization in terms of acid plus alkali, it produces water. But the reason why ammonium salts making ammonium salts is neutralization is because you're adding acid to an alkali. So it's either acid to a base or acid to alkali, or it's an acid to a base, acid to an alkali, and you create water. Now, if that's the case, we can go to the next one. Reactions of acids with bases. Acid plus metal oxide goes to salt plus water. And again, we've highlighted the spectator ions, and we can do our ionic equation. So again, you can do any number of these, and you can put in different acids, and you can put in different carbonates. You can just practice writing them out. You don't need to ask a question. Just change this for a potassium carbonate, for example, or aluminium carbonate, or something like that, or a copper carbonate, and then change the acids around. Now, strong and weak acids. Again, just a reminder from last year. Strong acid is fully dissociated, so make sure you remember that from last year. Okay, and they're your examples that I expect you to remember, which is hydrochloric acid, sulfuric acid, and nitric acid. Now, a weak acid is partially dissociated. Okay, so that means that only some of the acid is turned into H+ ions and its conjugate base, whereas in these examples, all of the acid is changed into its conjugate base and the protons. Now, examples for both. These are your examples for the strong acids, and carboxylic acids are generally your weak acids. You will go into much more detail in future videos about the difference and the problem with assigning acids with this title of strong and weak. And we'll go through a way of calculating pH with a strong acid and calculating pH with a weak acid. Now, bases and alkalis, just remind you again, a strong base is fully dissociated, okay, and they're hydroxides, okay, and then you get a weak base which is partially dissociated, and again, that's things like carbonates and such and so forth. But again, we're not going to do the pH in terms of working out of a weak base in this course, we're just going to do the pH of a strong base, and we'll do that in the following videos.